Hi class, my name is Sarah Wilkins. This is for Advanced Group Concepts presentation number 2. We're going over how to derive the Michaelis-Menten equation. So the equation itself is going to describe the reaction once equilibrium is reached. So we have an enzyme by itself, and then we add a substrate, and that binds, which is known as that enzyme substrate complex. We have the rate constant, which is K, but once the complex begins to form, it is going to dissociate back into reactants, and the reverse is the K minus 1, the K negative 1. Okay, and using that rate constant of the K2 and the K minus 2, you see how they're going in different directions. So we have one going forward and then we have one going backwards, and the same for the K1 and the K negative 1. So this essentially is the reverse, the one that is going back. And by using this, we're going to form the product. So as enzymes catalyze reactions, the velocity versus the substrate rate can be plotted, and the curve shows that as the concentration increases, the velocity approaches the Vmax. So you'll see what I'm explaining there down at the bottom. This is how we can use that equation and plot it and graph it and kind of use it on another level. So that's really important there. All right, so as you can see on the left, there's 3 equations. These are the next 3 steps that we're going to use to derive that Michaelis-Menten equation at the end as our end result. So the first one here is the rate at which the enzyme transforms the substrate. This equals the product of the rate constant multiplied by the concentration of that molecule itself. The second equation is the rate of formation. So the rate of formation is of the enzyme substrate complex. And lastly, the third one is the rate of dissociation, which is of the substrate complex. That enzyme substrate complex is equal to the product of reverse reaction. So essentially, by using these, the rate of formation is going to be equal to that rate of dissociation. All right, and you can see 2 equations in that upper left-hand corner here. What we're doing here is taking that rate of formation we had just talked about in that last slide, and we're going to make it equal to that rate of dissociation. So the rate of formation is going to equate to that rate of dissociation. So this is an essential step here because we need those to be balanced or equal. Next, we're going to rearrange. So we're going to bring the concentrations to the left side of the equation, and then we're going to move the K values over to the right side, which you can see here. So if you look at the equation here, we have those K values on the right and the concentrations there on the left. So we're balancing, in this step, we're balancing that out. And this is actually called the Michaelis constant. Okay, and then we have the S total here and the E total here. So pretty much basically what's going on here. In the first equation, we're getting the total amount of the substrate that is within our beaker. So the amount of substrate that is not bound to the active site of the enzyme plus the substrate that is bound to the active site of the enzyme. And then for the E total here, we're getting the total amount of enzyme within the mixture. So the amount of enzyme not bound to the substrate plus the enzyme that is bound to the substrate. So we used that bottom equation here and plugged it into this equation here, which essentially gives us our Michaelis-Menten equation. So I hope this overview and kind of general idea of how we work through the steps and all the equations to how we get there makes a little bit more sense for this very complex process. Thanks, guys.